Hi, welcome to part 3 of the video series Deriving R Squared. Today we are finally going to discuss what linear regression is, and this concept will help us in the main derivation of R square. So let's start off. The first thing we're going to do is that we're going to combine all the concepts that we have discussed before. So first thing, I would recommend watching the previous 2 videos of the series because that will help you out in understanding today's video. Okay, now let's take the example we had discussed in part 2. We discussed this scenario in which you have multiple integer values or integer data on the costs of houses in Bangalore in the unit of tens of lakhs of rupees, 10 lakh rupees, that's the unit. Okay. Now let's take that scenario again. Let's say you had some data on a few houses within Bangalore and you knew their costs in the unit of 10 lakh rupees. Okay, so one would mean 10 lakh rupees, two would mean 20 lakh rupees, something like that. Okay. Now you go to this new house and you want to try and predict the house's cost. How would you do that? So in the last video, we discussed two mathematical tools that could be used, which were the mean and the variance. The mean told you about the central tendency, which means that what's the most expected value of the costs. Given the data that you have, what's the most expected value? So in the previous video, we had seen that the most expected value is 59. So you could say 59 comes over here. And the variance or the standard deviation helps you understand the spread of the data. Okay, why did we need the spread of the data? Let's recall that. The mean gave us this value, the middle value. But the thing is that different data sets could have the same mean. But the data sets may not be similar. Therefore, knowing the spread of the data is also a very important aspect of understanding how the data works. Hence, we saw that the standard deviation, which is basically the root of the variance, gave you a good value of how much the spread could be in the with respect to the mean. So for example, in that situation that we talked about with the Bangalore house data, we had seen that the standard deviation was around 78. So you could say that the houses in Bangalore would cost around this much, 59 plus minus 78. And this is in the unit of tens of lakhs of rupees. So what does this mean? It means that, let me take a different color to explain this part. 59 is the middle value. Now you could go this way 78 units and you can go this way 78 units. Okay. Now have a look at this. This is your prediction that the cost of this new house that you have found in Bangalore could be 59 plus minus 78. These numbers, if you calculate, are around 158 values that are possible. That is the main prediction that you can make using these two tools. And these are so many values. I mean, do you really get a precise enough prediction? Not really. This is when we come to the point that just knowing the costs of different houses within Bangalore, is that enough? Is that enough for us to be able to properly predict the cost of a new house that we find? So take a pause, think of this. Now scrap whatever we have learned up till now. Don't think of that. What if I were to take you to a new city? What if I took you to Mumbai and I told you that in Bombay, I'm showing you this house over here. What do you think the price of the house would be? Now think about this. What all goes on in your mind when you try to predict the cost of that house? If it were me, I would have thought of a few things. I would have thought of, the number of bedrooms in that house. One second. Maybe even before bedrooms, I'd first think, what's the location of that house? Then I would think of how big is this house? So what's the square foot area? Then I would think of the number of bedrooms that are there in this house, right? Then I'd probably think of the floor on which the house is. That also impacts the cost a lot. I would think of all of these things and then think of what the cost could probably be. Think of the expected cost. And I would then probably be able to get a better prediction, a more precise understanding of what the cost of the house could be. This is where we talk about increasing the precision of our prediction. Now, what we are going to try and do is we are going to try and say that the cost of a house is dependent on all these factors, on all these features rather. I won't use location right now. Reason is that location is something called a categorical variable, which means that location could be a city name. Now, city names, to make them quantifiable or numerical, there's a whole different way of thinking about it. I may put up a different video on understanding how to work on categorical variables. But for now, we'll take the three numerical variables that we talked about, which is square foot, area, number of bedrooms, and the floor on which the house is. So let's say that the cost is dependent on these three features. I'm going to write S for square foot, B for the number of bedrooms, and F for the flow. Okay. Now let's go back to a concept we had discussed in my first video series. I'll put a link to that video in the description box too. We had discussed functions. Now, what had we said about functions? That a function could have multiple variables also in it. So you could say that the cost of a house is a function of S, B, and F. S, B, and F being three different variables. So these three features are three different variables because their values can keep changing, right? This means that there is some sort of equation that is created using these three variables. So let's say that that equation is some sort of constant, let me call this A1 times S plus A2 times B plus A3 times F plus A4. Now over here A1, A2, A3 and A4 are all constants. Constants, the opposite of variables. These values will never ever change. So if A1 is equal to 5, it will always stay as 5. Okay. Now let's have a look at this briefly. We see that there is some dependence of cost on S, or the square foot area. There's some dependence of it on B, some dependence on F, and then there is this extra value that we have added. Now let's discuss this equation. We'll come back to this equation rather in the next slide, in which we're going to discuss something interesting. We're again going to bring together some topics we have learnt about. So let me open it up. Okay. Now have a look at this first equation over here. Y is equal to mx plus c. Y is equal to mx may be familiar. I would recommend watching the first video of this series because in that you will be able to understand what y is equal to mx means. I'll talk about it briefly over here. M over here indicates the slope and c indicates a constant value. Okay. Now, why did we add this constant? How is this constant value going to affect everything? Let's have a look at that. So if you remember, even in the first video, we had a look at this line called y is equal to 2x. Okay, and when we differentiated it, we found out that the slope is equal to 2, which makes sense. If you see, the coefficient of x is 2 and the coefficient of x is supposed to be the slope. Yeah. Okay. Now have a look at this second line. It's still y is equal to 2x, but you're adding a 3 to this. This 3 is a constant. Now just observe this graph. These two lines are parallel to each other, but their angle is still the same, which means that y is still changing at the same rate with respect to every unit change in x. Now let's think about this a little more. Let me just change the color. Okay. So let's have a look at different values of x. Okay. And we look at these two equations. This is equation 1. This is equation 2. Okay. I'm just going to write it here. 1, 2. And now we're going to look at different values of x. So at x is equal to 0, what's the value of equation 1? In the sense, what is y's value in equation 1? 2 times 0, which is equal to 0. And what about 2? Y is equal to 2x plus 3. So y is equal to 2 times 0 plus 3, which is equal to 3. Now let's have a look at what happens when x is equal to 1. When x is 1, the first equation is equal to 2 times 1, which is 2. The second equation is equal to 2 times 1 plus 3, which is equal to 5. Now let's have a look at the third value of x. Let's say x's value is 2. This means that the first equation's value would be 2 times 2, which is 4. And the second equation's value will be 2 times 2 plus 3, which is equal to 7. Now have a look at the difference between the different values of x and y. So for every unit change in x, when x goes from 0 to 1, the first equation's y value also changes by 2 units. And so does the second equation's y value. Even the second equation's y value is changing by 2 units. Now let's look at the second interval when x changes from 1 to 2. Here too, equation 1's y value changes by 2 units, and so does equation 2's y value. So you see, the rate of change is still the same. For every unit of x, both the y values change by 2 units. But there is a minimum value added to this 2x. Now let me give you an example for that. A real life example. Now, if you live in India, you would have sat in a rickshaw. Especially if you've sat in a metered rickshaw, then this will make a lot of sense. So in metered rickshaws, what generally happens is that you have a base amount to pay. Generally, with what I remember, it used to be 20 rupees. Okay. Now what happens is that you have this base amount. So even if you do not make the rickshaw move but you have booked it, you'll have to pay 20 rupees. That's the base amount. It's like, the initial deposit in when you're buying something, when you're buying a house or something like that. Okay, so you pay an initial of 20 rupees. Then after that, based on the amount of distance that's traveled, a certain rate is added each time. So for example, if it's rupees 10 per 100 meters, per 100 meters, then you'll keep adding rupees 10 per 100 meters. So let's say, let me give you an example. Let's say somebody rode a rickshaw for 500 meters. Okay. So that would be rupees 20, which is the base, plus the rate of the rickshaw moving 500 meters. So if it's 10 rupees per 100 meters, that means you would have to pay 50 rupees total. Okay. So this is equal to 70 rupees. Okay. Now, if you see, the rate per 100 meters would be the same no matter how much this initial value was, which means that the change in the cost of the rickshaw per 100 meters will still stay the same. It doesn't matter what this initial cost is because the rate is still the same. So you could start off from anywhere, but if the rate is the same, the change will be the same. That is the main concept behind adding a constant value. So have a look at it over here too. Let's say if you went on 600 meters, the total would have been rupees 20 plus 60, which is equal to 80. And you can see that the change is 10 rupees per 100 meters, which was at initial rate, 10 rupees per 100 meters. Now let's say that the initial cost instead of 20 rupees was, let's say, 10 rupees. 10 rupees initial cost and 10 rupees per 100 meter is the distance wise cost. Okay. In this case too, what would happen is 500 meters would just be rupees 10 plus rupees 50, which is equal to rupees 60, and 600 meters would be rupees 10 plus rupees 60, which is equal to rupees 70. So the change in the total cost is still 10 rupees per 100 meters. I hope that makes sense. Also, just as an additional challenge, try differentiating or using the fundamental theorem of calculus to find the slope of this equation too, y is equal to 2x plus 3. You'll notice that the slope is still the same. It's still 2. Because if you remember, a constant getting differentiated is equal to 0. Therefore, only 2x would remain, and 2x is the derivative of 2x is just 2. Okay, so give that a try. Try it out. You can use video number 1 of this series. It'll help you out in differentiating this this equation of a line. Okay, so now that you've understood what a constant means, let's have a look at this equation over here. If you notice, this equation here is very similar to what we talked about in the previous video. A1 x1, where x1 was s, E2 x2, where x2 was I think it was bedrooms, yeah, bedrooms, and you would have an x3 which would have been equal to floors, so f. Okay, instead we've just taken a common variable name. That's the only difference over here. And here, instead of saying that there are only 3 variables, we are saying that there are, let's say, n variables. In that sort of a case, each of these n variables would have their own slopes. Think of it in that way, that how much is y's value changing with respect to just the first variable. So for every unit change in x1, how much is y changing? That is what is represented by A1. A2 represents the rate of change of y with respect to x2. Okay, so you could think of them as individual slopes, that how does y change, or how does the cost of a house change just with respect to a unit change in the square foot area of houses, or just with respect to the change in the number of bedrooms in 2 houses. Okay, that is what all these coefficients of every variable mean. You could also think of it in this way, that each coefficient, A1, A2, so on, also indicate how much that variable impacts the cost of y. How much the variable, I'm just going to write the short form, variable impacts y. Okay, that's what it means. Now, if you notice over here, because there are n variables, you would have one value, 1a n plus 1, that basically indicates the constant value. because the constant is always possible, right? We saw even in the previous one that a constant is always possible even if there's one variable. It's possible if there are two variables, so on. We just add this term. This term could even be equal to 0. Because if you see over here, when you write y is equal to 2x, it's kind of like assuming that it is y is equal to 2x plus 0, where the constant is 0. Think of it in that way. Okay. So now, just to give you an extra fact, this equation over here is kind of like saying that you are drawing a line in n plus 1 dimensions. So if you notice y is equal to 2x, or any equation of this kind where you just have x and y, is drawn in a 2D plane. Okay, so if you have n variables, if you add y also to this, to the plotting of a line, you would have n plus 1 dimensions. Just an extra fact to think of. And actually drawing a line within those many dimensions is very tough. It's tough to even imagine. That's why I haven't put in anything about that over here. Okay, so now we have discussed what those variables were, what the coefficients are, why is the constant important. Let me now get back that equation. Cost is equal to A1S plus A2B plus A3F plus A4. And now we come to what is linear regression. Linear regression is a method of finding out how much do all these three variables actually impact the cost, or rather what is the best approximation of A1, A2, A3 and A4, such that if given a new house, you could find the closest cost possible, or you could predict the cost as well as possible. Yeah, as close to the actual cost as possible. That's what linear regression is. It helps you create an equation based on the data that you already have. It helps you create an equation, and this equation helps you predict the y value of a new set of values for those three variables. So this means if you had all the values available, or rather all these variables value available for let's say 10 houses, you could use those values to create an equation, find a great approximation for A1, A2, A3 and A4 to create your equation, and then use that equation you've created to predict the cost of a new house. So if you went to that new house, you would just substitute S, B and F with whatever is available in that new house, and A1, A2, A3, A4 would have already been found out. You would calculate this entire value and and try to predict the cost of the new house. Okay, I hope that makes sense. It'll start making even more sense in the next video when we talk about linear regression in more detail and we start the actual derivation of R square. Okay, so for now, this is it. One last thing actually that I wanted to tell you about is that in the next video, we are not going to talk about multiple variables. We're just going to take a simple equation, which is y is equal to, you could say mx plus c or a1x plus a2. Either way is fine, mx plus c. And we are only going to try to find a method of finding the most optimal values of m and c. And this is called simple linear regression. I'm just going to write LR to represent regression. It's called simple linear regression because only one variable is used, that's x. If you used multiple variables, x1, x2, x3, so on, it would be called multiple linear regression. Okay then, so that's it for today's video. I hope You have a great week ahead, and I'll see you in the next video of this series. Bye bye. Have a nice day.